Good afternoon, everyone. Today we're going to factor two different polynomials. The first one using algebra using the rectangles and squares, and the second one just by hand. So for the first one, we have 4x squared plus 6x, right? So we can think of what is the greatest common factor of each term. So the GCF of 4x squared and of 6x is, well, what's the greatest common factor of 4 and 6? Of course, that's 2. And then what's the greatest common factor? That is to say, the biggest number that we can factor out of x squared and of x, or the biggest number that can divide x squared and x, well, that'll be just x, right? We can't be x squared because x is smaller than x squared, right? X squared is 2 factors of x. So we can only pull out 1 factor of x for which term, okay? So the greatest common factor of the two terms is 2x. So we know that this is gonna factor out to be 2x bracket something, and rather than just do it by hand, let's actually use the algebra tiles. So we know we need to draw in total 4 big x squares and 6x, 6 of the rectangles. Let's use the green for positives. So we're gonna have one dimension. Because the GCF is 2x, then we're gonna have one of the dimensions, whether you consider it to be the length or the width, really doesn't matter, you can choose. Let's make the width 2x, right? This is 2x. Then we can create nice x squares out of those two, right? Because we know 1x squared has dimensions x times x, right? X times x, so 1x, another x makes a width of 2x, right? And now we need to draw 4x squares and 6x's in total. So since we have 2x squares already here, we can draw 2 more attached below. So that will give us the 4x squares that we want. And now we want to make it a nice rectangle when we're done drawing it all out. So we have 6 x's to draw in a way that makes a nice rectangle. We can either draw them below and wherever we want. I'm just going to draw them on the side because we have more space. We have 6 of them in total. It looks like we have 2 nice rows to split them evenly into. So let's make 3 rectangles in each row, like so. So that means 6 x's divvied up into 2 rows. And now, oh, you know what? Since I drew them sideways, let's adjust that. Let's say that now we'll have this dimension be 2x, right? That's one length of x, that's another length of x. So together, that's 2x for the length. And now the width is 2x plus the x rectangles are a length of x and a width of 1. And so the width of 3 little rectangles are simply 3 units, right? So we get 2x, x plus 3. And that's our length, right? You can see why. When I chose to draw the rectangles on the side, because I had more space, we could have interchangeably drawn them below the squares, and then the 2x would have been the width, the 2x plus 3 would have been the side length. It would have worked out exactly the same, right? So we get one dimension of 2x. We already knew that. The other dimension is 2x plus 3. And so there we go. That's our polynomial in factored form. You can multiply through just to check that you get this right back. 2x times 2x recreates 4x squared, and 2x times 3 recreates the 6x. And so here's our polynomial in factored form, okay? For the second one, we're just factoring, let's say by hand, right, abstractly. So we're looking for the GCF of all 3 terms. We can only factor what is common to all 3 terms. Can't get greedy. So what is the biggest factor of 21, 30, and 42? Of course, that's 3. For the x's, what is the greatest power of x that we can factor out of all 3 terms? We have 2 powers of x here, 4 powers of x here, and only 1 power of x, right? Because x is implied to be x to the power of 1. So the only factor of x that we can factor out of all 3 terms is x, right? We can't factor anymore because this one only has 1 power of x, okay? Now the y's, we have y to the power of 1, y squared and y to the 11, sorry. So what is the greatest power of y that we can factor out of all 3 terms? Again, the limiting one is this one, right? We have only one measly power y, so that's all we can factor out of all three terms. And we're left to leave everything else inside of the brackets. So 3xy times what would recreate 21x squared y, 3 times 7, and x times x would create x squared, and we already have a factor of y, so we don't need any more. Plus 3 times 10, x times what would create an x to the power of 4, x times x cubed, right? Remembering our exponent laws, when we multiply two of the same base, we add the exponents. So an exponent of 1 plus 3 would recreate the exponent of 4 in the original term. And y squared, we only have y to the power of 1 here, so y times y would create that y squared. Right? No, whoopsies. Sorry. That y squared that is in the original polynomial. Y times y is y squared. Okay. And finally, 3 times 14 gives us that 42. X times what becomes x? We don't need to multiply by anything, right? X is already itself. And y to the power of 1 times what becomes y to the power of 11. Again, when we multiply by the same base, we add exponents. And so we need to add 10 to the 1 to make it 11. And so y to the power of 10 is our last term inside the bracket. And there we go, we're done. We factored out a GCF of 3xy, and this is what we have left inside, okay? Hope this helps. Thanks for watching. Take care.